Hello, everybody. How are you all doing? I hope you're doing well. I really do. We're looking at question 6 now in this video on our 2019 MMC. What have we got here? In triangle ABC, angle ABC is acute, M is a point on AC, and we know ABM is equal to CBM. Okay, so BM is the angle bisector. And we want to prove what? BA is to BC as MA is to MC. Okay, this is actually a result, I believe, called the angle bisector theorem. And they're just asking us to prove it. Okay. So how are we going to approach it? So we know that we've got the same angle here, maybe call it theta. So we want to find a way to relate the fact that these two angle thetas are the same. We'd like to be able to relate that to the ratios of the sides. So what can we possibly do? Well, where do you really see angles and side length ratios? You don't see them directly, but with the sine law, you do see. For example, remember the sine law, of course. ABC, ABC. We know that A is to B as sine A is to sine B. And that gives me a ratio of sides and not necessarily an angle, but the sine of an angle. So we could BM, A up here, C, and I think B, no, B and M went across. B was in the middle. Okay. So we could say, let's look at this triangle up here. Now, what sides are we interested in the end result? We want BA. Eventually, that's going to compare to BC, and they also wanted MA. Okay? So we could say by sine law, BA is to MA as the sine of AMB, the angle opposite BA, is to the sine of my theta, which we're calling ABM. Okay? So that uses this angle here. We've also got this angle here. What else can we do? Well, we can do the same sort of thing, but down in this triangle here. And again, what sides are we interested in? MC and BC. So I don't know if I want a particular way of doing this, but we'll say BC is to MC. I might want to flip that in a moment. We'll see. Is to sine of what's opposite BC? CMB. And sine CBM. Okay. Now I know that this angle and this angle are the same. That's what they tell me in the question. But what about these angles? Well, there's one of them here and the other one here. They add up to 180. So what do we know about supplementary angles? Angles that add up to 180 when it comes to sines. Okay, well, you might recall that sine of 180 minus an angle is the same as sine of that angle. If you were taught with the unit circle, you might remember this. If I imagine sine for this angle up here, sine is the heights of these little right angle triangles you make inside the circle. It's the same as if you went back, because you get two congruent triangles, and so you'll get the same heights and therefore the same sines. Okay? So I can see that angle AMB is 180 minus angle CMB. And so the sine of AMB is the same as the sine of CMB. So BA over MA is sine of AMB over sine ABM. Now the bottom, the two angles inside the sines are equal. And on the top, we've got angles that are supplementary. So their sines must be equal, even though the angles themselves aren't. And we get this, which I don't think is what we were asked for, but I think we can quickly rearrange. Yeah, BA to BC. I'd say rearranging. We get BA over BC is MA over MC as desired. And there we go, nice little proof of the angle bisector. I can't remember if you can do it without trig, but the trig just sort of jumped out at me. How to work with angles and side ratios. Really, sine law is sort of the first thing that should come to your mind there. Okay, and that's it for the question, right? It was just prove that. Yeah. All right, so there's question number 6. Join me for question number 7 as we continue our Manitoba contest in the following video.